Hey there, aspiring pilots and aviation enthusiasts. I am absolutely thrilled to have you here. If you've got a passion for aviation and you're ready to really understand what's happening when you're flying, well, you are in the exact right place. Think of this explainer as your essential pre-flight ground briefing. As your instructor today, my whole goal is to guide you through the fundamental weather theory that literally every successful aviator has to master. We're going to break down these concepts step by step, making them super intuitive so you can confidently take to the skies. All right, let's get started.
So before we ever turn a propeller or fire up a jet engine, we have to stop and ask ourselves a pretty basic question. What exactly are you flying through? You know, it's so easy to look up and just see empty blue space, right? But the air is a dynamic, physical medium. It has actual weight, it has distinct layers, and it behaves according to some very specific rules. Understanding this invisible ocean of air is absolutely crucial. It's the key to mastering your aircraft.
Okay, here's our flight plan for today. 1. Layers of the atmosphere. 2. The engine of uneven heating. 3. Invisible forces shaping wind. 4. The three-cell circulation. And 5. Pilot temperature conversions.
Section 1. Layers of the atmosphere. Let's dive right into this first phase by examining the immediate environment we climb through the second our wheels leave that runway.
The atmosphere is defined by altitude and specific characteristics at various levels. But first, let's look at the actual composition of dry air. It's mostly nitrogen, about 78%, and oxygen at 21%, with other gases making up that remaining 1% plus moisture. Now, starting right at the bottom, we have the troposphere. Just above that is the stratosphere, which extends way up to about 160,000 feet or 50 kilometers. The stratosphere is known for having very little weather, highly stable air, and temperatures that initially change very little before actually increasing as you get higher. Beyond that are the mesosphere and the thermosphere, but honestly, those have very little influence over the weather we experience as pilots. So our primary focus is going to remain lower down.
That brings us back to the troposphere. This is our true playground. It's where almost all weather, clouds, and temperature variances happen. It extends from sea level up to about 20,000 feet over the north and south poles, but it actually swells all the way up to 48,000 feet over the equator. Now listen up, because as an aviator, you absolutely must commit these standard lapse rates to memory. For every 1,000 feet of altitude you gain in the troposphere, the temperature will predictably drop by 2 degrees Celsius, and the atmospheric pressure will decrease by 1 inch of mercury. Lock those numbers in your head.
Marking the very top of our flying environment is a critical boundary layer known as the Tropopause. You can basically think of the Tropopause as the ceiling of the troposphere. Because of the really distinct temperature changes that happen up there, it effectively traps moisture and weather right beneath it, keeping all that action contained within the troposphere where we fly.
Now, why does this matter to you practically as a pilot? Well, it isn't just a perfectly flat static ceiling. It actually has an elliptical or oval shape, meaning its altitude varies constantly depending on your latitude and the season. In our middle latitudes, it usually averages somewhere between 36,000 to 37,000 feet. Crucially though, the tropopause is commonly associated with the location of the jet stream and possible clear air turbulence, or CAT. Knowing exactly where this boundary sits helps you anticipate rough air before you ever hit it.
Section 2. The engine of uneven heating. Let's see how solar radiation acts as the ultimate engine for atmospheric circulation, or, what we normally just call wind.
The fundamental reason we even have wind is the uneven heating of the Earth's surface by incoming solar radiation. Specifically, we're talking about the massive difference in heating between the super warm equator and the freezing poles. To make this easy, let's imagine a non-rotating Earth to understand pure convection. Air is heated at the surface, right? That heat creates more space between the molecules in a given volume. This makes the air less dense, so it rises. This rising action literally leaves a void, creating an area of low pressure down at the surface. That heated air continues to rise until it finds air of a similar temperature, reaching equilibrium. Once it can't go any higher, it journeys north and south toward the poles. Eventually, it cools down, becomes dense, and descends, creating high pressure, before flowing right back toward the equator along the surface to replace the rising air. It's an incredible cycle.
To put that into perspective, let's look at how uneven heating works on a local scale. During the day, the land heats up much faster than the water next to it. This causes the air over the land to become less dense and rise. There's our convection. But to fill the low-pressure void left behind, cooler, denser air from over the water rushes in over the land.
That horizontal movement is called advection. Together, this entire process creates what we know as a sea breeze. But at night, the whole system just flips completely. See, land doesn't just heat faster than water, it also cools much faster. So as the sun goes down, the land cools rapidly while the water is still holding on to its heat from the day. Now, the warmer air over the water rises, and the cooler, denser air from the land flows out toward the sea to replace it. And just like that, you've got a nighttime land breeze. Section 3. Invisible forces shaping wind. Heating might get the air moving, but other forces dictate exactly where it goes. The very first force at play is the pressure gradient force. Because of the pressure differences we were just talking about, air naturally wants to flow away from areas of high pressure and into areas of low pressure. If you're looking at a weather chart, this force acts perpendicular to the isobars. Those are the lines connecting areas of equal pressure. The golden rule here for pilots is super simple. The closer those isobars are grouped together, the stronger the pressure gradient force, and that means you can expect some seriously strong winds.
But here's the catch. The air doesn't just flow in a perfect straight line because the Earth is spinning. This introduces a really fascinating concept called the Coriolis force. It's a real force caused by the rotation of the Earth, and it causes any straight path of moving air to curve. In the northern hemisphere, it deflects air to the right, and down in the southern hemisphere, it deflects it to the left. The strength of this Coriolis force is actually greatest at the poles and drops all the way to zero at the equator. Also, keep this in the back of your mind. The faster the speed of the wind, or your aircraft, the greater that deviation is going to be.
Think about it like this. Imagine you're trying to fly in a straight line dead south from the North Pole. As you fly, the Earth is quite literally rotating eastward beneath you. By the time you reach your target latitude, that Coriolis deflection has pushed your actual path noticeably to the right of where you aimed. Every single pilot navigating in the Northern Hemisphere has to constantly account for this persistent rightward drift. The final force we need to discuss is the friction force. This one is caused by the physical ground surface of the Earth rubbing against the moving air. This effect is incredibly powerful, but it's mostly limited to within 2,000 feet of the ground. Friction slows the wind speed down, and because wind speed decreases, remember what we just said, the Coriolis force also decreases. Importantly though, friction does not affect the pressure gradient force at all. You are vividly going to feel this drastic shift in wind dynamics within that bottom 2,000 feet during every single takeoff and landing you do.
Section 4. The three-cell circulation. Now we see how all these invisible local forces scale up to massive global patterns.
Let's zoom way out and see how this all builds into the global three-cell circulation model. Because the Earth rotates, that simple single-cell convection model we talked about earlier gets totally broken apart. Instead, the interaction of pressure, Coriolis, and friction creates three distinct, massive circulating cells in each hemisphere, spanning from the equator all the way up to the poles.
All right, let's trace the journey of this air. Starting at the equator, we have the tropical or Hadley cell. Warm air rises at the equator and pushes north due to the pressure gradient force, but the Coriolis force deflects it to the right. By the time it hits 30 degrees latitude, the Coriolis force perfectly equals the pressure gradient force, and suddenly the air is moving eastward. It cools and sinks right there, creating a high pressure zone. As it flows south along the surface back to the equator, Coriolis deflects it westward, but friction reduces that deflection, ultimately giving us the northeast trade winds. Next up is the mid-latitude or Ferrel cell. Some of that sunken air at 30 degrees flows north along the surface. Right around 60 degrees, it smacks into cold air flowing down from the pole. That sharp temperature difference forces the air to rise up and circulate back to 30 degrees, which results in our prevailing westerlies. Finally, the polar cell. Cold, dense air at the pole flows south along the surface. It meets that 30-degree air at the 60-degree latitude mark, gets forced to rise, and circulates right back to the pole, generating the polar easterlies. It's like a giant, perfectly synchronized machine.
Section 5. Pilot temperature conversions. As we near the end of our explainer briefing, let's switch gears for a second and cover a really vital piece of mental math every aviator needs in the cockpit. So, aviation weather is reported globally in Celsius. But depending on where you're flying or what specific older instruments you might have in your panel, you might need to convert to Fahrenheit on the fly. To make a quick, reliable estimation, just use this simple equation. Take the Fahrenheit temperature, subtract 30, and then divide by 2. Trust me, it is incredibly handy to have this shortcut when you have a million things going on in the flight deck. Now, I need you to pay very close attention to these specific testing parameters based on our source material. For Celsius, frozen is 0 degrees, and boiling is 100 degrees. For Fahrenheit, boiling is 212 degrees.
However, while we commonly use 32 degrees Fahrenheit for freezing in our daily lives, for your specific exam parameters, you are required to note 23 degrees Fahrenheit as the frozen mark. I'll say that again. You must memorize the listed 23 degrees Fahrenheit figure for your testing requirements. Make sure you keep this exact number locked in for test day.
All right, we have covered a ton of ground today. We've explored the atmospheric layers, the incredible engine of convection, the invisible forces of pressure and rotation, and the global winds they create. So my final question to you is this: how are you going to use this atmospheric knowledge on your very next pre-flight check? Because the next time you look up, you won't just see empty blue space anymore. You're going to visualize lapse rates, pressure gradients, and Coriolis deflections. If you apply this knowledge before you ever leave the runway, you are going to become a safer, far more capable pilot. Thank you so much for joining this explainer today, and as always, I wish you clear skies and tailwinds.